Welcome back. So we've just proven some results about uniform limits of sequences of functions. Namely that the uniform limit of a sequence of functions, sequence of continuous functions rather, preserves continuity. So if you like, the property of continuity is preserved by uniform limits. Moreover, if you have a sequence of continuous functions and a limit point in the domain of that sequence of continuous functions, then at that limit point you can switch the order of limits. Those are the two theorems that we just proved. So using this fact, let's go back to these questions that we asked. If a sequence of functions is continuous for all n, and f is the pointwise limit of fn, then does it follow that f is continuous? No. No, it does not. If you take the sequence of functions f sub n of x equal to x to the n on 0, 1, then these suckers are all continuous and they converge, but their limit is 0, 1. So, not continuous. On the other hand, if you have a sequence of continuous functions, and f is the uniform limit, does it follow that f is continuous? Yes, that is exactly what we just proved. Let's check that that reference is correct. Yes, 4.2.1. Suppose that the limit as x goes to c of f sub n of x is equal to L sub n, and the limit as n goes to infinity of L sub n is equal to L. Does it follow that the limit as x approaches c of f of x is equal to L? Said another way, is it true that we can switch the order of limits? And what we found for some sense of last time, studying this same sequence, if I take the limit as n goes to infinity of the limit as x goes to 1 from below of x to the n, I get 1. But if I take the limit as x goes to 1 from below of the limit as n goes to infinity of x sub n, I get 0. These two things are not the same. So, in general, can we switch the order of limits? Nope. But if we add the condition that f sub n converges uniformly, yes. Theorem 4.2.2. Wonderful. So, the last thing I want to talk about is another way of understanding what uniform convergence means. I'm going to introduce the so-called supremum norm on the space of functions. So, this last video is going to be, if you like, a segue into what is functional analysis. So what we've done so far in this class is we've done analysis on real numbers. We've studied distances between them, we've studied functions on real numbers, but we've done analysis on the real numbers themselves. What if we take the set of all of the, say, continuous functions on real numbers? Can we do analysis on that? Can we talk about functionals on the space of real numbers? Can we think about operations which take functions and return functions? And you know a few of those already. You know that, like, integration is one such operation. Differentiation is another such operation. Can you study those operations and ask if they're continuous? Well, to ask if they're continuous, I need to be able to measure the distance between functions. And one way of doing that is by the sup norm. So I'll go off to the side. So the sup norm, d for distance, sub sup, between two functions f and g, is going to be the supremum of all of the differences between the inputs. Absolute value of f of x minus g of x, where x is in, I don't know, the domain that you're walking over. Both of these functions are defined on some domain u. So, not the interval from 0 to 1. So the following theorem will detect that uniform convergence can be detected in terms of the supremum norm. So if you have a sequence of bounded functions, and f is another bounded function, then f is the uniform limit of this sequence of functions f sub n, if and only if the sequence given by taking the distance between all of the f sub n's and f's using the sup norm, converges to 0. And this will be actually a reasonably straightforward result. This last video is supposed to be kind of an invitation to what is functional analysis. Let's study some of it. So let's let f sub n from u to r be a sequence of bounded functions, and f from u to r be a bounded function, so I'm just declaring the assumptions that are in the theorem. Let's let s sub n be the sequence given by the sup of f sub n of x minus f of x, where x is in u. So notice, if, say, f sub n or f weren't bounded, then that set might not be bounded. And so this supremum would just be infinity. Or I guess we haven't defined what it means for the supremum to be infinity in this class, but that's what you would want it to be. So I'll just add the word bounded. The reason I add that the word is bounded is all over the place, is to ensure that that supremum is finite. So let's now prove two things. Let's suppose that f is the uniform limit of f sub n. I need to show that s sub n converges to 0. So let's think about how to do that. Let's do a sketch. So I want to show s sub n converges to 0. That is, we need to show that for every epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, s sub n, absolute value, why not, is less than epsilon. So a few things to notice. S sub n is the supremum of a set that only contains non-negative things. So I automatically know that s sub n is positive, so I'll just erase that. So I really want to show s sub n is less than epsilon. So I know what s sub n is. So if I want to show that s sub n is less than epsilon, what do I really need to show? I need to show that the supremum, because s sub n is a supremum, of the set of all things that look like absolute value of f sub n of x minus f of x, such that x is in u, I need to show that that is less than epsilon. And how will I show that that's less than epsilon? Well, maybe this will seem kind of artificial. I'll show that it's less than or equal to epsilon over 2. And maybe I'll tell you why that's a reasonable thing to say. I know what it means for a supremum to be less than or equal to a number. If I can show that a number is an upper bound on a set, then the supremum, being the least upper bound, will be less than or equal to that number. So all I need to show, well, what do I need to show to prove that? I need to prove that epsilon over 2 is an upper bound on the set of all things that look like absolute value of f sub n of x minus f of x, where x is in the set big U. But how do you show something is an upper bound? To show something is an upper bound, you need to show that it's at least as big as everything in the set. So I want to show for every x in U, absolute value of f sub n of x minus f of x is less than or equal to epsilon over 2. So now we're cooking. I know how to, what do I know about the sequence of functions? The sequence of functions converges uniformly to f. So, by uniform convergence, there definitely exists a big N such that for all little n bigger than big N, absolute value of f sub n of x minus f of x is less than epsilon over 2, which will in turn imply that this is less than or equal to epsilon over 2. So epsilon over 2 is an upper bound. Since epsilon over 2 is an upper bound, that means the supremum is less than or equal to epsilon over 2, which is strictly less than epsilon. That means s sub n is less than epsilon, but s sub n was already positive, so I can put those absolute value bars back. So over here, I see a sketch of the proof. I guess the sketch goes backwards, but that's okay. We can now write it forwards. Oops. So let's do it. Consider any epsilon bigger than 0, because f is the uniform limit of the sequence of functions f sub n, and we see that there exists some big N such that for all little n bigger than big N, absolute value of f sub n, for all little n bigger than big N, and for all x in U, absolute value of f sub n of x minus f sub m of x. So I've made that mistake an awful lot during the course of recording. I've put a little m there because I really want to be talking about the uniform Cauchy condition, but that's not today. That difference is less than epsilon over 2. But notice, that means that epsilon over 2 is in fact a proper upper bound, it's not in the set, on the set of all things that look like f sub n of x minus f sub m. I did it again. F sub n of x minus f of x. Did I include any of those errors after this side? I mean, I did plenty of times. I had to re-record that like 5 times. I don't want to re-record this one. So epsilon over 2 is an upper bound, but the supremum is the least upper bound. That means that the supremum of the set of all things that look like f sub n of x minus f of x is less than or equal to epsilon over 2, which in turn is less than epsilon. So, what have we shown? We have shown that, well, we started by considering any epsilon bigger than 0. I then came up with a choice of big N, and I considered any little n bigger than big N, and concluded that S sub n is less than epsilon. Since S sub n is greater than or equal to 0 for all n, we see that the absolute value of S sub n is in fact less than epsilon. And maybe just putting one final sentence, one final word, thus, absolute value of S sub n minus 0 is equal to the supremum of, well, you can read it from here. Thus, the limit as n goes to infinity of S sub n is equal to 0, as we claim. That proves the forward direction. Let's prove the opposite direction. On the other hand, let's assume that S sub n, the limit as n goes to infinity of S sub n, which is to say the limit as n goes to infinity of the supremum of this set of all things look like f sub n of x minus f of x, where x is in U, that limit is equal to 0. And what do I want to show? I want to show that the sequence f sub n converges to f uniformly. What does that mean? That means I want to show, for all epsilon bigger than 0, there exists a choice of big N, such that for all little n bigger than big N, and for all x in U, absolute value of f sub n of x minus f sub m, nope, no m, f sub n of x minus f of x is less than epsilon. That's what I want to show. Well, one thing that I definitely know is that absolute value of f sub n of x minus f of x, that's an element that's in the set of all things that look like absolute value of f sub n of x minus f of x, where x is in U. And the supremum is an upper bound. So that means that this thing, those are ditto marks, is less than or equal to S sub n. But S sub n converges to 0. So I should be able to pick a little n big enough and I think that would do the trick, right? So let's write that down. Let's assume that limit of S sub n is equal to 0. Consider any epsilon bigger than 0. Then I know that epsilon is what I'll eventually want. There exists some big N such that for all little n bigger than big N, the absolute value of S sub n minus 0 is less than epsilon, so that in particular, S sub n is less than epsilon. Now I'll consider any little n bigger than big N, because I just came up with my big N, now I have to consider any little n bigger than that, and any x in the domain U. Then, as we said to this side, the thing that we want to show is small is an element of this set. And so, because the supremum is an upper bound, we see that the absolute value of f sub n of x minus f of x is less than or equal to s sub n, which in turn is less than epsilon. which is S and epsilon, by 4.8. Hey, that's exactly what we needed to show if we wanted to show that the sequence converged uniformly. Radical. So I hope that this series of 3 video lectures has been useful in understanding a few of the properties of the uniform limit. I'll talk to you again real soon.